Hello everyone, this is the editorial for problem E of CodeCraft-22. So I assume everybody's read the statement, so I'll just skip reading it line by line and just give a brief overview. The problem essentially asks the problem essentially gives us n horizontal segments that are laid out on the number line. So each of these segments have their each of these segments start in n coordinates or integer coordinates, and the segments are assigned some color. The color is either red or blue. This is a binary assignment, and for every pair of segments in the given set of segments, we perform the following operation. If the segments are of different colors and they intersect each other, then these two segments are connected to each other and they become part of the same group. So if you consider the sample over here, segment 0 and segment 1 are of different colors and they intersect, so they're connected to each other. The same goes for segment 1 and segment 2, and segment 3 and segment 4. But notice that while segment 1 and segment 3 intersect each other, because they're not of different colors, they're not connected to each other. So after all the operations are applied for every pairwise comparison of segments, we're left with two groups of segments that are formed. So the question essentially asks how many groups of segments have been formed after we've done all possible, after we've connected all possible segments. So the first thing to notice is that the range of L2R, the coordinates of the start and end points of all the segments, is of the order 1e9. So it's not feasible to iterate over L2R. However, n is 1e5, and it's we can take this as a hint that we have to work with segments over here to solve this problem. Well, to solve this problem, let's consider this example. Now, to give us some sense of making progress, let's iterate from left to right, right? So let's say I sort the segments by the points at which they begin, and I start iterating over my segments from left to right. What I can start doing is I can merge segment 1 with segment, like when I reach segment 1, I would merge it with segment 2, 5, and 6. Now when I'm at segment 2, I would merge it with 3, 4, and 1 again if I wanted to. And then when I reach segment 3 after this, I would then merge it with 2, 5, and 6. And I can start merging segments one by one like this. But again, this solution has n-squared complexity. The problem is we're making a lot of connection operations, and we cannot afford to make n-squared connection operations. So we want to figure out if there's a way to somehow go over this set of segments without doing n-squared connection operations while still having the same number of groups. Also, to iterate, initially I'd mentioned that iterating over all points from L to R is 1e9, and we cannot simply iterate over all L to R and all integer coordinates, that is. But instead of iterating over all integer coordinates, we can break up a segment into sets of 2 points: the point at which the segment starts and the point at which the segment closes. So this would give us exactly 2 endpoints to go through, and this is with n complexity. We can iterate over the set of all points at which segments start and end instead of iterating over all integer coordinates. So now let me define what I mean by an open point. To solve this problem, I want to maintain sets of segments which are open. What I mean by an open segment is essentially, let's say I'm at some point here. So let's say while iterating from left to right, I encounter the point 1. So I'll put it in the set of open blue segments. Now when I reach point 2, segment 1 is still open. That is, I have not reached the closing point of segment 1 yet. So an open point essentially refers to a segment with which I'm intersecting. Like, because essentially I'm adding these points to the set when I'm iterating from left to right, and removing them when I reach their close point. So, for example, this would go something like me adding 1, then 2, then 3, then 4, and then after adding 5 and 6, I would come across point 1c, at which I would remove 1 from the set. So when following an approach like this, when I reach point 2, point 1 still existing in the blue set means that this segment has not terminated yet at point 2, and it's still and it exists. So that means I'm intersecting with it at some point. Now let's try to go back to our original algorithm and see what it does. So when I reach point 1, I add point 1 to the blue set, and then when I go to point 2 after this, I'll add point 2 to the red set. Now, when I add point 2 to the red set, I notice that the blue set is not empty. there's a point here, which means there's a segment I'm intersecting with of the opposite color. So I'll merge segments 2 and 1, or connect them. Sorry. Now the next point I come across is point 3. Point 3 notices that there's a point open in the red set, so it connects to segment 2. The next point would be point 4, and again, when I add 4 here, it notices that there's a 2 in the red set and connects to 2. Now the next point I come across is point 5. For 5, there's 3 points in the blue set, so it would connect with point 1, 3, and 4. Let me do this in a different color. So it would connect with 1, perhaps yellow maybe. Okay, that's not good. Let's try purple. So it would connect with 1, 3, and with 4. But I'm still leaving 1, 3, and 4 in the blue set. That means when I come across point 6, I would again have to connect it to points 1, 3, and 4. So the next point I would come across is point 6. And when I'm adding point 6 here, I would have to again connect it to 1, 3, and 4. And this isn't good. I'm connecting it to components again and again, and this would have n-square complexity. Is there something I can do to reduce the number of connections I'm making? Notice that when 5 connected to 1, 3, and 4, 1, 3, and 4 all become part of the same group. So any set of segments that are still open in the blue set, when connected to 5, become part of the same group. So when I'm connecting 6, it would suffice to connect 6 to just any of the previous segments that 5 connected to. If 6 connected to 1, that's enough. 6 does not have to connect to 3 and 4 both. Connecting to all of them is just a waste, because after the connection that 5 makes to 1, 3, and 4, 1, 3, and 4 are all part of the same group. Connecting to a single segment is the same as connecting to all the segments. So to do this, to achieve this kind of goal, can I perhaps replace 1, 3, and 4 with a single segment while still ensuring correctness? The answer is yes, because now, because 1, 3, and 4 all belong to the same segment, it suffices to connect to just the last segment that terminates. So the existence of 1, 3, and 4 in the blue set means that these segments exist at that particular point and will continue to exist until they reach their closing point. In this case, that would be 1C, 3C, and 4C. So as long as the segment that gives me the best chance of connecting to the 1, 3, 4 group is simply the segment that terminates the last. So here 4C is that segment. If I'd replaced 1, 3, and 4 with 1, and I had a red segment over here, it would not be able to connect to 1 to join the same 1, 3, 4 group. However, the rightmost point that this group 1, 3, 4 can reach is the last point that any one of its segments terminates at, which in this case would be 4C. So I can replace the set 1, 3, 4 with just 4. This is the key optimization that lets us solve this problem in faster than n square. Because now, for each segment, I would just connect it once when I reach the open point, and I might connect it once in between when a segment of the opposite color connects to it. But again, whenever the opposite set gets length greater than 1, it gets it can get squashed into a list of just size 1. So over here, after 5 does its combinations, I have just 4 left in the previous set. Now the next point I come across would be point 6. 6 connects to just 4. So 6 only connects to point 4. It does not connect to segment 4. It does not connect to segment 1 and segment 3. So from here on forth, we're pretty much set, right? There's only one connection made over here, and when the next point I'll reach is point 1C, there's nothing to remove in the blue set, so it just skips it. The same goes for 3C, and when we come across 5C, we'll remove 5 from the set. 4C, we remove 4 from that set. Oh, I forgot 2 in between, but it removes 2 from the set as well. And that is about it. This simple observation lets us solve this problem in n log n time complexity. While the solution is relatively straightforward and we can build up to it, implementing it is not as easy. This was my original solution to the problem. I solved it by using a DSU data structure to maintain a number of components. The connection operation here, as you might have realized, is very similar to just a DSU merge. So we can just use a DSU merge operation to track the number of components. Now, I'm maintaining points in a vector of set. Defined a struct for pointer and with a overloaded operation for comparison, which just compares the point on the number line by the starting, which is the point coordinate. And I'm iterating through all the points in my set. And whenever I see a point that indicates the opening of a segment, I'll just insert it into that particular running set, and I'll go through the opposite colors running set, and I'll replace them with and I'll just replace it with whatever is the largest element over there, while also unifying it with all the segments over there. While this is what made sense to me at the point we made the question. There's also an easy solution here, which DocSign has on his e-solution. Since we're replacing the entire set at any given point, we don't even need to use a set over there. We can shave off log n complexity at that portion by just using a vector and just replacing the vector with the max element over there. If you see the code here, he just replaces the opposite colors running set with just a max element over there, and that's also just as fine. We incur cost of allocation memory over there, but otherwise it should be faster on time complexity for this region. The overall time complexity will still be n log n thanks to the sorting of the points. That's it for the solution.